Here's Chapter 10 material. This is worth studying as well. This is largely based on the ideal gas equation, so pay attention to these sorts of problems. Lots of conversions. This first problem right here is fairly direct. Convert the pressure 0.840 atmospheres to millimeters mercury. How are you going to do that? Well, 1 atm, 1 atmosphere, is equal to 760 millimeters mercury. So we're prompted with 0.840 atm. Set up the dimensional analysis, in which case we now go to 1 atm is equal to 760 millimeters mercury. Well, essentially this is, well, 0.840 times 760, which we could go ahead and say, we could look at this as 84%. So 84% of 760, well, it's going to be less than 760, so we can cancel out D. 437 divided by 760, drawing a relationship between those numbers, you know that this is close to half. And likewise 365 is significantly lower than 760, so we are left with C as our only really viable answer for this question. So 0.840 times 760, that's what you're going to end up getting. A sample of oxygen occupies 560 milliliters, so right off the bat we are given a volume. 560 milliliters. Let's go ahead and convert that to 0.560 liters. But let's continue. A sample of oxygen occupies 560 milliliters when the pressure is 800 millimeters mercury. At constant temperature, what volume does the gas occupy when the pressure decreases by 700 millimeters mercury? It decreases to 700 millimeters mercury. Okay, so what we have here is an interesting scenario. With this problem, what we can do is basically what we're simply asking is, what is the new volume? So when our pressure, so we have one scenario in which case pressure 1 is equal to 800 millimeters mercury, 760 millimeters mercury is 1 atmosphere. So we'll convert that. Calculator, 800 divided by 760 equals a pressure of 1.05 atm. Our volume number 1 is what we defined earlier, 0.560 liters. At constant temperature, so our temperature doesn't change. However, our volume does. What does it change to? So we have a new scenario where we have a new pressure. It's 700 millimeters mercury. 760 millimeters. Is 1 atm. 700 divided by 760 equals 0.921 atm. Our V sub 2 is unknown. With this, when we have constant temperature and we know nothing about our sample, the amount of our substance doesn't change. So we have, I'm going to put fixed temp. We also have fixed amount of substance. What we can do is say P1 V1 equals P2 V2. So we could wrap this up as 1.05 times 0.560 divided by 0.921. And ultimately our V sub 2 is going to be our volume 0.638 liters, or 638 milliliters, which our closest answer for that is answer B. This problem asks us to calculate the approximate volume of a 0.600 mole of or sample of gas at 15 degrees Celsius and a pressure of 1.10 atmospheres. Now, one thing that's significant and worthwhile to remember is what we see right here, our sample of gas. This says nothing about the, no specifics about the gas, so the identity of the gas is completely irrelevant. But that's just something worth noting. So in order to solve this problem, we have to be familiar with PV equals nRT. This is the ideal gas law. Now, we have some of these values already defined. So first of all, our N is going to be 0.600 moles of our unidentified gas. Again, the identity of the gas is completely irrelevant. Temperature. Well, our temperature must be measured in Kelvin. So if our temperature is presented as 15.0 degrees Celsius, what we want to do is we want to add 273.15 Kelvin. So that brings us to 288.15 Kelvin as our temperature. The pressure is 1.10 atm, which whenever we're measuring pressure for the ideal gas equation concerns, well, we want it in units of atmospheres. So we have our pressure, we have our number of moles, we have our temperature, we also actually have our R value, which is 0.0821. Okay, so we have all of these. We are left with, or we do not have our volume. All that we need to do is basically rearrange this equation and put volume by itself. So basically, we rewrite this equation as V equals nRT divided by pressure. So we can plug our numbers in. Volume is equal to 0.600 times 0.0821 times our temperature, which is 288.15, and divide all that by, well, 1.10. So simply by being able to basically manipulate that algebraically, you're going to be able to answer this problem. 0.6 times 0.0821 times 288.15 divided by 1.1 equals our volume of 12.9 liters. 12.9 liters. Do we have any answers that reflect that? Yes, we do. Answer option A is our correct answer. So this problem right here, a 1.00 liter sample of a gas has a mass of 1.92 grams at STP. What is the molar mass of this gas? Okay, now to answer this problem, the first thing that you need to do is you need to remember PV equals nRT, our ideal gas equation. But it's not necessarily that direct. There are a couple of things to consider. Well, first of all, let's go ahead and take up all the information, or use all the information that we're presented with. We have a volume of 1.00 liters. We also have, so 1.00 liter sample of the gas, we also have standard temperature and pressure. Well, STP, standard temperature and pressure, gives you a couple of things. First of all, the temperature is 273.15 Kelvin. The pressure is 1 atmosphere. So by being associated or being comfortable with STP, you know your pressure, you know your volume, you know your temperature. You also know your R value, which is R equals 0.0821. Now the sticking point is, and essentially what this question is asking, is what is the molar mass of this gas? What we need to do is we need to recall that N is equal to the number of moles, and that is equal to the mass of a substance, or G, divided by the molar mass of that same substance. So what we can do with this information is carry this on and write PV equals, rather than N, we write this. PV is equal to G divided by MM RT. That is the same as writing this. PV equals GRT divided by MM. Okay, so now to solve for, well, the molar mass, what we need to do is get MM by itself. So we multiply both sides of this equation right here, multiply both sides by MM. That will cancel, and we're left with MM times PV equals GRT. Okay, divide each side by PV, pressure and volume, and you're left with, those will cancel out, you're left with, we'll move this up here, MM, our molar mass of our unknown gas, is equal to GRT over PV. Now we have everything that we need. So molar mass is our unknown, MM, is equal to our grams, our amount of our unknown gas, which is 1.92, times R, which is 0.0821, times our temperature, which is 273.15, out. We divide that by the only two values that we have left, our pressure and our volume, which is 1.00 times 1. So 1.92 times 0.0821 times 273.15 equals our molar mass of 43.06 grams per mole. So of our answer options, 1.92, that's off the table, 19.2 off the table, 22.4, D, 43.0 is our correct answer. Chlorine is produced by the reaction of HCl yielding H2 plus Cl2. So this is a decomposition reaction. How many grams of HCl must be used to produce 10 liters of chlorine at STP? Okay. So this question right here is more or less asking kind of an elaborate or an indirect way. It's getting at the ideal gas equation. PV equals nRT. Now what we have here is we have, again, standard pressure and temperature. We have a pressure, it's 1 atmosphere. We have a temperature that is 273.15 Kelvin. We have a volume that is 10.0 liters. We have an R value that is, well, that R value is still the same, 0.0821. Okay. Now, what we want to do, we want to look at our N value as what we want to solve for. We also need to refer to our balanced chemical reaction. So what we want to do is we want to rearrange this equation so that we isolate N. So PV over RT equals N. So this will allow us to solve for the number of moles of chlorine that are produced in this scenario. So what I'm going to say is I'm going to write this out as, well, 1 atmosphere times, oh, sorry about that, 1 atmosphere times our volume, 10.0 liters, divided by our R value, 0.0821, times 273.15. All of this is equal to 10 divided by 0.0821 times 73.15. This is all equal to N, which when you plug it in your calculator, you figure out that this is 0.4459, so I'm going to call it 446 moles of what? Well, Cl2. Okay. So what we can do with this is we can look at our balanced chemical reaction. So how much, the question is asking, how much HCl is required to make 0.446 moles Cl2. Okay. We know that 2 moles of HCl will produce 1 mole of Cl2. Therefore, 1 mole of Cl2 is produced by 2 moles of HCl. So, what we can do is set up 0.446 moles Cl2, do our dimensional analysis to bring in our balanced chemical reaction. 1 mole Cl2 is produced by 2 moles HCl. Now what we want to do is relate our 1 mole HCl to our molar mass, 36.5 grams of HCl equals. So this would tell us, this gives us our molar relationship, and it ultimately tells us the mass of HCl that we're going to utilize to produce that. Okay, so 0.446 times 2 times 36.5 divided by 1 equals 32.558, or 32 point, let's call it 6. Do we have anything like that? Well, we have 15.8, no. 30.2, no. 36.5, no. Answer option C looks to be the correct answer.